Recording is rolling. It's Tuesday, January 18th, back from a 3-day weekend. We got a nice short 4-day week going on here. Oh, you guys I have a new quiz for you. Looks like this, clip to the front of your desk, simple harmonic motion and waves quiz, front and back. This is going to be open notes take-home quiz, just like the most one we've been doing this year. Let's have that due the Monday coming back from this next weekend. So that's 6 days from now, Monday, January 24. Okay? Will be when this quiz is due. You guys also have chapter 13, 14 puzzles look like these. Due this upcoming Friday, January 21st. Now we've done most of those in class. I still have a couple of those to go over in class, so get those eventually. Got a starter question here involving some springs we'll take a look at here in a minute. The main thing for today is going to be AP Classroom Unit 6 multiple choice questions, which you guys finished by today. We'll get most of the way through these. Some other stuff I want to cover, but we're going to have to save some of this other stuff for another day. Let's start with this question over here, which actually is going to lead into the first few questions for AP Classroom Unit 6, which is really nice setup. Let's say you got a spring hanging vertically from a ceiling. So, and this says unstretched. So it's just hanging out. There's no force on it. Okay? And then we're going to take a mouse, maybe like one of these guys, and just flick it right there and just let it go. And it's going to fall down to some maximum distance, call it X max. And then it'll boing, spring back up, and it'll oscillate just back and forth. Boing, wow, wow, wow. Then let's say after so many cycles, after about a minute or so, let's say there is some frictional loss, and it eventually settles at some equilibrium position. I'll call it X equilibrium. Okay? So you got X max versus X equilibrium. And my question is, what is the ratio of these two? What is X max compared to X equilibrium? Okay? Well, maybe you might ask, well, what framework would you use to solve for either of those? So a hint, how about one of these you're going to need conservation of energy, and the other you're going to need forces. Right? So I'm thinking that you would need conservation of energy to solve for X max, because at the top, like when you first hang the hook mass to this unstretched spring, it does have some vertical height above the lowest point. So that'd be like having some gravitational potential energy. When it reaches the lowest point, all the energy would have gone into the spring. See, if you define this lowest point as height 0, it has no gravitational potential, but it does have a bunch of spring potential. It's a bunch of energy stored in that stretched spring. But at each of those locations, there's 0 kinetic energy because it's at 0 speed here. And at the bottom, it's like turning around. It's maxed out and it's about to turn around. Okay, so conservation of energy would be really good for this one. But when it eventually settles to some equilibrium position, I want to use forces. We're going to set up a free body diagram, say the force up equals the force down, it balances out, zeroes out, and then solve it that way. All right, let's see where this is going. Solve this one first. We're going to use our energy framework, conservation of energy. So if energy is conserved, sum of energy initial equals sum of energy final. Remember, that's for a closed system. What is in the closed system? I'm thinking the mass, because the mass can change height and move. There's the spring, because energy can go into the spring, something to do with 1/2 kx squared, but also the earth, because if the earth is providing it, and otherwise what would be an external force? This would be an open system if you did not include the earth. So got to include the earth because there's a gravity force on this mass. Also, this mass is changing height relative to the earth. So what kind of energy, I got to pick my two locations, initial, final. Let's go initial right here, just as you're hooking the mass on, and final is at the point where it's maxed out and it's about to turn around. So I'm thinking that it's all gravitational potential here. It's some height above its lowest point. That's mgh. But instead of h, I'm going to let that be x max because that's the total distance it could fall. And we're eventually going to solve for that. Mgh, but mgx max. Okay? By the time it gets to the final point, down here, where has all the energy gone? Well, there's no kinetic. It's not in motion. I mean, it's turning around. Okay? At that moment, there's no motion. There's no gravitational potential because that's defined as lowest point. It's all in the spring. It's all 1/2 kx squared, where k, of course, is the spring constant. How stiff is the spring? Okay. Oh, and this is x max. Okay. So we got that. Now you guys see that x max is going to, well, one of them is going to cancel out. So this cancels out with this power reduces to 1. Okay. And we're solving for this right here. So a couple of algebra moves, cross multiply this 2, divide down k. X max equals 2 mg over k. There you go. If you know mass, the gravity field, and the spring constant, you can figure out the maximum distance it'll go before it oscillates back. Remember, it's oscillating back and forth between these 2 points. But eventually, frictional losses, it'll settle to some point. Well, what is that point that it settles at? Well, now we're going to use a different framework. We're going to use forces. Right? We're going to set up a free body diagram. So here's your free body diagram. I'll do FBD, free body diagram. And so I'm thinking of 2 forces on this block. There's its weight pulling down, that'd be mg. And there's the spring pulling up. And well, that's Hooke's law, kx, right? Spring times x. And this x would be the equilibrium x. Okay? So if it's at rest, that's an example of equilibrium where the sum of the forces would be 0. This is 0 newtons. This is in the y direction if you want to be strict about that. And what are the 2 forces? Well, they're right here labeled on the free body diagram. So you got kx acting upward. You got the weight acting downward. And those 2 have to balance out. You might say, okay, these are equal and opposite forces. That's true, but not because of Newton's third law. These are not in Newton's third law of pair. The equal and opposite force of the weight pulling down is this block pulling up on the Earth. The entire Earth is being pulled up with an equivalent amount mg. And the equal and opposite force to kx, the block being pulled up, is this block pulling the spring down. These are equal and opposite because of this equilibrium condition. This x is the equilibrium position. And that's what I'm interested in finding. I'd like to know what that is. Well, I see a couple of algebra steps to get there. Algebra steps. I'm going to add over the mg and divide down the k. So x equilibrium is equal to, let's see, mg divided by k. Okay? Hold on to this idea. Notice that I haven't given you guys any numbers. I didn't tell you what the mass of the block was, the spring constant, or even what planet we're on for that matter. You could hop planets and still use those. These are general solutions. But now you see what we're getting at. What is x max compared to x equilibrium? That's the question. Okay. Here's x max, here's x equilibrium. See how it's a 2-to-1 ratio? And because this is a general solution, that's always going to be true. So x max is equal to 2 times x equilibrium. And that is the answer to that question. Good tidbit to know that could totally pop up on AP exam or something like that. So 2 different frameworks dealing with springs. Okay. Rest of class, we're going to be looking at AP Classroom Unit 6.